Good afternoon. My name is Gerald Allgaier. I'm Systems Specialist for Vitrek, and I will also be joined by my colleague Andrew Dawson, Engineering Manager and Application Specialist. And we'll be going over the GaGe brand of products that can be applied in the semiconductor industry. So our GaGe brand is known for our high-speed digitizers that can capture and digitize high-frequency signals with high resolution and accuracy. In semiconductor manufacturing, they're basically essential tools for capturing and analyzing fast electrical signals with high fidelity. And they enable engineers to basically observe and measure the behavior of devices and circuits in real time. And that provides valuable insights for like design validation, performance analysis, and troubleshooting. Their high performance, including maximizing the effective number of bits over a wide signal frequency range, help provide real-time data on the device performance and behavior, thereby improving the efficiency and accuracy in the manufacturing process. And them being PCIe-based devices, our digitizers can be easily integrated in open PC-based platforms with the capability to stream acquired data in real time to either host CPU or GPUs for signal processing and or signal recordings. So in the semiconductor industry, our high-speed digitizer usage generally falls into three main categories, and that is real-time process control, material inspection, and functional testing. For real-time process control, it's the fast download speeds of the acquired data that allow for the rapid real-time characterization testing of the semiconductor fab process. And here, the advantage of our digitizers is their short data latency that allows them to participate in fast device control loops. For the material inspection, our digitizers are generally used as a part of a non-destructive test system to effectively inspect wafers for potential flaws or defects. And here, the advantage of our digitizer is the ability to capture signals at high speed with high resolution for digital analysis. And in the functional testing, that's where chips are basically rapidly positioned into test fixtures, where there are high-speed test signals that are acquired at key test points, and the chips under test are either flagged as being pass or fail. And here, the advantage of our digitizers is their rapid download speed with the ability to quickly switch ranges for fast test switching. In the next couple of slides, my colleague Andrew Dawson is going to review some of the specific customer use cases for each of these categories with our digitizers.
Hi, Andrew Dawson here. I apologize, point of order here. We've got some construction going on outside, so I'll try and speak over that. As Gerald said, I'm going to take you through about a half dozen applications here. We'll sort of go through the semiconductor manufacture process and highlight the applications in which the GaGe card finds itself. I should say that our GaGe digitizers are very general purpose, and we don't really have any specific features for semiconductors per se. But as you'll see, we find the GaGe card in quite different applications at many different stages because of its very general purpose ability to capture high-speed waveforms from different sorts of probes. So to begin, we'll talk about this real-time. This is right at the beginning at the semiconductor fabrication facility. So they start with what you may have seen, a raw semiconductor wafer. These are typically, I think, about 1 foot to 2 feet in diameter. These are the biggest and most pure single crystals of any element that we can make. We've been making pure single crystals of silicon for so long. We're really excellent at it. And what they do in these fabrication facilities is deposit impurities into the pure silicon to dope it, as we know, N and P type doping, and to build various complex structures, processors, and so forth. So basically, they deposit this onto this large wafer, and then afterwards saw it up into little pentiums or whatever they are. The GaGe card is used to control one of these deposition, a piece of deposition equipment. Normally, the GaGe card is used to acquire data and then analyze the data in post-processing, where there's no real rush to get the data analyzed. This, however, is what we call a real-time application, which is kind of defined as one where you need to get the answers. You need to analyze and reduce the data, kind of get the answer as the measurements are occurring, because you're actually having to act on it. One particular example we always bring up is when you're in your plane and there's a missile bearing down on you and you want to spoof it. You've got to read the signals from the missile and react quickly to spoof it before it blows you out of the sky. So similarly here, as the very fast deposition equipment is going along, it's got to be controlled based on feedback signals from certain sensors. So the customer has 8 sensors and originally started out with our 8-channel card streaming the data continuously. So this customer will take like one trigger and then acquire continuously for literally days as this process of deposition continues. And initially, as I say, they were acquiring the data and getting all the raw data off the card, which is the card was particularly perfectly capable of doing. But it turned out it was this like fire hose of data, which they couldn't manage. They couldn't process the data quickly enough to be able to consume it all. And indeed, we're only able to analyze about 10% of the data. So they'd take a chunk of data, analyze it and reduce it, and then they'd miss 90% of the rest of it, and then take another chunk. So this, presented problems for their closing their feedback loop. So what we did for them, our cards are controlled by what we call an FPGA, a field programmable gate array. Normally, instrument cards like ours would be controlled by a much simpler and general purpose multiprocessor. The problem is we need to move data around our cards so quickly from the ADCs to the memory and to the PCI bus at rates of several gigabytes per second, and you just can't do that with a microprocessor. So the FPGA is more like, it's a big chip that is more like configurable circuitry, software configurable circuitry. So instead of data moving around as controlled by a CPU, it's more flowing through circuitry in a pipeline fashion, which can be move data hundreds and thousands of times faster. Now, this FPGA is less than half full with sort of standard GaGe functions. And up until maybe 15 years ago, we just concentrated on getting the raw data to the user as quickly and as easily to use a fashion as possible. But we started putting in, for that 15 years, started putting in data processing firmware. We call it firmware because it's in between software and hardware. And we've got several canned firmwares that the customer can obtain. One for example, signal averaging, one for FFTs, one for digital down conversion, and others. What I say is that the FPGA is really good for data reduction, for separating the wheat from the chaff. In the farming business, right? They literally separate the wheat from the chaff before sending the grain to the mill, and that's because they don't want to pay for the expense of transporting the useless chaff to the mill. The more refined operations, grinding and so forth, are done at the mill, but you really want to get that weight down. In a similar way, the FPGA is best used for getting rid of the garbage that you don't want, so that only the data of interest are relayed across the PCI bus to the customer. So in this example, the firmware that we developed for the customer picks out things like amplitudes and zero crossing positions of the waveform. And you can see how if you have thousands of points and reduce that to a single amplitude, you can get huge reduction factors. And indeed, we were able to achieve a reduction factor from this data that's coming in on 8 channels at 500 megasamples per second. We achieved a data reduction factor of about 150. And by doing that, that reduced the processing load on the host CPU. It had to deal with 150 times less data, and this pre-processing step, the burden of this pre-processing step was alleviated. So by doing that, they were able to go from consuming and processing only 10% of the data to consuming 100% of the data, and that worked in their was able to work in their control loop. Another angle of this real-time application that isn't obvious and isn't relevant in post-processing applications is the data latency. How fresh is the data? Okay, because if the data is too old and you're trying to control the process on it, you might be sort of closing the barn door after the horses left the barn, sort of thing. So we were able to achieve with this firmware, because it's so fast, latencies of only a few milliseconds, sorry, which was sufficient for the customer. So really, that went from an application without the firmware that couldn't be done to one that could be done with the powerful effect of this data reduction firmware that, as I say, reduced the fire hose of data to a sort of a drip, drip, trickle. So moving along, as I say, from the fab process, the next stage is inspection of chips of the dies during packaging. So the next application here is an important one. One of the main functions of the package, other than getting the connections of the electrical connections on the die out to the user, is for dumping heat. So the silicon die, it's again been chopped up from the fabricated silicon wafer, has to be well bonded to the package so that it can dump its heat. So what this customer builds is an ultrasonic inspection system to assess the bonding of the silicon die to its packaging. And the way it does that is when bonding is really good, sort of the interface between the two components being bonded, in this case the packaging and the silicon die, isn't there, and the sound goes right through the bond. However, if the bond is lousy, if the glue isn't sticking, or if there's some sort of delamination, this presents a reflective interface for ultrasound. So in fact, the amplitude, if you look at the place where you expect, you sort of know where to expect the echo from the interface between the die and the package. And if you look there, the amplitude of that echo is a direct measure of the poorness of the bonding. You can then scan parallel to the die surface, and then produce a map, a color-coded map of the bond quality over the entire surface of the die. And if it's, you can actually produce a kind of an average bond quality index that then is used to produce a pass-fail criterion for the chip. In the scan, which might be several thousand points by several thousand points, the data are streamed off of the card very quickly. In the old days, you'd have to stop, download the data, whereas now with our streaming technology, we're able to offload the data from the card as it's being collected for the very fastest scan time. So that's another big advantage of the GaGe card, is its fast data transfer speed for fast scanning. And of course, the high resolution to get the very smallest echoes from that bond to really judge that bond quality as best as we can. Next. So this is an interesting one, again, during the fabrication of MOSFET chips. So you package up your MOSFET chip, and in order to characterize it, you can run relatively expensive characterization techniques like X-ray or ultrasonic inspection. But this customer does a fairly novel technique to judge the quality of the MOSFETs. The MOSFET is excited in various ways by DC and AC signals, and then they listen to the device listens with the GaGe card to the noise signals coming out of various pins on the MOSFET, and specifically the frequency spectrum of the noise. And certain noise spectra can indicate signatures of key failure modes. I don't know to what extent that they actually understand why these noise, certain failures lead to certain noise signatures, or they might just do it phenomenologically, right? You can create a bunch of chips with known defects and then just look at if they look any different than regular chips. Anyway, as I say, it's very important that the card, they use a 4-channel card, 16-bit card to get the very best signal fidelity on 4 channels so that you can run 4 chips in parallel at the same time. And it's very important that the card has a very good frequency flatness, because you want any frequency variation that you measure in the noise spectrum to be indicative of what's going on in the chip and not on the card itself. So that's an important demand that the card met for that reason. So that's our second inspection application during the fabrication of chips. Moving on. Now we have a couple of functional tests. That's where you take the finished chip and put it into some sort of jig and see if it works as it's supposed to. In this case, the customer makes DC power conversion chips that, amongst other places, find themselves inside your telephone charger. Indeed, I think they brag that, not unlike spiders, you're never more than 6 inches or 12 inches or something from one of their chips, even though you might not recognize their name. So they have one particular test on their power chips that requires the chip to trip at a certain limiting current. So they, at relatively high speed, they ramp up the current, and then basically the line should be open once the current exceeds a certain very precise value, which of course they turn into a voltage to measure with our card. So they use actually one or more of our 4-channel cards so that they can probe 4 chips in parallel testing. They have an elaborate a chip mounting system that gets the chip into the jig, and they can do 4 or 8 at a time. And so in our case, our high resolution and very high DC accuracy was very important to them to measure that trip voltage, which corresponds to a trip current, very accurately, and also our ability to allow multiple digitizers to work together seamlessly so that they can test several chips at the same time. Next. Yeah, next slide. There we are. Okay, so people who, too far. People who've worked in the semiconductor industry may know the curve tracer. Okay. Sorry, can you hear me?
Yes.
Okay, I'm back a couple of slides there, but I'll start anyway, right? The one on the curve tracer we're on, I'm seeing the digitizer products here. So I'll continue. The curve tracer is a device that that applies control, normally applies DC voltages to a transistor chip and then measures currents. And typically there's a couple of control voltages and one measured current. So you may have seen one of these analog devices way back in the 60s or even earlier. Looks like an oscilloscope, but it produces these elaborate traced curves that characterize the transistor. So as I say, normally it applies DC voltages, but this customer makes a device for users characterizing silicon dies in R&D. And as we learned in the previous application, an unpackaged die has problems in that it overheats. It doesn't have anywhere to dump its heat. So basically, when these researchers are making candidate transistor dies, they can't hook them up to a conventional curve tracer to characterize them, because they don't have the capacity to dump their heat. And so if you applied the DC voltage the conventional curve tracer does, the die would overheat and burn. So rather than forcing the researchers in R&D to go to the trouble of packaging their chips, what this customer does is makes a curve tracer that only applies a very short pulse instead of DC voltages. So it might apply a pulse of a microsecond or two every millisecond, thereby reducing the power that's applied to the die by a factor of 1,000 to where it doesn't overheat. So they can measure the same curve tracer curves except without overheating and burning the die. So, so for that they embed our digitizer within the instrument that they sell, and they need four. I believe each one needs at least 2 channels, but they do use. So I think it's 2 channels times 2, so that they can use. Uh, they can do multiple chips at a time. I may be wrong about that. It may be 4 channels per chip, and then they use multiple cards embedded within their device. And of course, having the 16 bits and high accuracy is important for this measurement, because they do actually measure absolute voltage quantities, which they turn into currents and so forth. So that's an interesting application. Next, I believe, is the last one, which is a customer of ours that makes magnetoresistive disk read heads. Okay, these would formerly, before the 1990s, have been a very small coil to read the magnetic domains on the hard drive. Nowadays, we use something that was discovered in the 90s, or maybe a little earlier, developed in the 90s, which is something called giant magnetoresistance. The slides one ahead, if you could run that one back. So both sorts of reeds heads, the old coil and the magnetoresistive head, actually, it's interesting. I always assumed that a disk drive, the inner cavity, was evacuated to avoid air pressure. Apparently not at all. There's gas in there, because the head actually flies like an airplane wing, glides over the surface of the disk, and only flies at a couple of nanometers above the disk in order to get the greatest resolution. The closer you are to the disk, of course, the smaller domain you can write and read. So what they do then is, in manufacturing testing, they run the hard drive, and they read back signals from a known pattern written on the hard drive, and compare it to what the known pattern is. But at the same time, they can look at the raw read head voltage with the GaGe card and make sure that that's right. So they use it during development as well, to develop their disk reading algorithms, but also in production for quality assurance. Again, they use a 4-channel digitizer, so they can run 4 of these heads in parallel. We actually developed also for them, custom firmware that allows for calculation of a data histogram on board the card, since all they need ultimately is a histogram to determine the nature of the signals that come off. The histogram is enough to characterize basically the head, whether it's a pass or a fail. So with that, those are the 6 applications that we could come up with for the semiconductor industry in those 3 domains we discussed. With that, I'll pass it back to Gerald for some information on the GaGe cards.
So here's our table matrix of our current digitizer product models, detailing the A to D resolution that go from anywhere from 8-bit to 16-bit. Number of input channels from 1 to 4 channels per card. You can have multiple cards in the system. The maximum sampling rate per channel from 250 megasamples per second per channel, all the way up to 6 gigasamples per second per channel. Amount of onboard memory from 2 gigabytes to 16 gigabytes, depending on the model. The PCI interface type, and the current starting at pricing for these model families. All of our digitizers come included with our GageScope Lite Edition PC oscilloscope software, and that package does not require any programming. It's a GUI-based application that any customers can utilize with the products to visually see their acquired data. And they also come complete with our full library of software development kits that include C, C#, Python, LabVIEW, and MATLAB. And these software development kits are utilized by our customers to develop their own customized applications that are optimized for their specific requirements. The SDKs come with pre-built examples complete with source code that are fully commented for the developers to follow to make it easier for them to start to develop their custom applications.